now I've got the neutron detector switched on, which would help to have a neutron detector switched on. So it's down, so just turn that down. I don't think it does anything. It's hot. Yeah. So when I get this 1 ohm resistor, which is a 50 watt resistor, should work lovely for a few days. And if we bring the voltage, the sensitivity of this thing down to 2 volts to 3 volts, there's a slight, that's mains frequency hum, which is present all the time in all circuits as far as the mains. And since it's tuned to 50 Hertz, that is always there. So that's nothing. So 200 volts, nothing at all. Right, that's all. Thanks for happening now. This trace is the trace. The upper trace is the output of the resonance coil, which is 169 volts at 50 Hertz, which is the mains frequency. It's driven from the mains. It's driven from a mains transformer, and there's a drop-in resistor of 10 ohms, a 10 watt 10 ohm resistor to prevent the current from rising. It takes a current of 1 amp into the primary coil that drives it, and the primary coil gives a voltage, which you can't see, of 2 volts, about 2 volts, about 2 volts. That's the total voltage, and so it's only about 2 watts going in. So it's quite small. It was running at 12 watts as well. And this lower one, the lower trace, is the neutron detector. I fixed the fault on the neutron detector. It was one of the joints was not connected. It was dark. The earth terminal was connected. Which was the case. It was a connection. So that's the lower trace. So that's not doing anything. And as I say, before the voltage increased, and this could be due to failure of the transformer, something's getting through, or there was something happening. I don't know. But it's powered by the mains, which means it's not producing power itself. But it could be producing power itself as well, but I don't know what happened last time. But it's not happening this time. I'm taking careful measurements this time. Be careful. So leave that around. It's actually making a noise because the 10 watt resistor is getting hot. And it's not quite enough power. I mean, 10 watts at 1 amp, 10 ohms at 1 is 10 watts. So it is a 10 watt resistor, so I should take it. But this is the other gigawatt, it goes up. It's not very. That's the other gigawatt. It's just nothing happening. Nothing happening at all. So not very interesting. And I don't know what happened last time. I was tired and it was recording, but I'm sure the neutron detector goes somewhere that it's only stopped, and it's not doing it now. The neutron detector was undamaged by its experience, and so there's the trace. So it's a nice sine wave, but the circuit is going to is tuned. It's a capacitor and inductor, and it's tuned to 50 Hertz, so there should be no phase lead or phase lag, and so it shouldn't be through a meter. But if you have an inductive load or a capacitive load, the power meter doesn't read correctly, so do be careful. It's illegal to have inductive loads, and I've done everything possible to make it not an inductive load. There is a transformer, a main transformer, which is a commercial one, and there's a choke, which is quite a small choke, if you mark around this, to stop area, and that drops about 20 millivolts. So it's not very much. And then there's the switch on the showing off the no voltage. It's 12 volts in, but it's dropped by 10 amp resistor. And the circuit is set to 1 amp. And I don't want to run it at that power because I know 12 amps is too much for the wire. I have got the wire it's run with is rated at about 5 amps. If you're lucky, it's quite a thin wire, and so it wouldn't take the current in 12 watts, 12 watts for a 12 amps ratio. So I did have a running on 12 amps for short time, so that means it was running at 144 watts. Rather than what it with the power is only what it's 1 amp at 1 amp at 2 watts, so it's 2 watts, it's much less. And I hope to get a 1 ohm resistor, a voltage of 10 ohm resistor. I have a 2 ohm resistor, but that resistor got rather hot. And I can run it out. I've run it out for a while because the resistor will overheat. It's actually 2 ohms at it goes to 3 watts. It's only 6 watts. It should actually take it. It should actually take it. I'll try it. I'll try it. It's actually getting hot now. I can hear I can smell the plastic burning. And it's the plastic, it's not anything else. It's the plastic, it is getting hot. The whole thing's getting hot. So, sorry about it. I know which one it is. It's that one. It's just getting hot. It could be improved by having it's getting quite warm. It's not overheating, it's just hot. And that's normal for electric circuits. But the vacuum sheet won't take it. I can now switch it over to the other. But I don't have a metal plate will fit on it. It will put that on. This thing on this wire. It's right, very thin. I'm going to set the high voltage. Okay. It's very hot. Very hot. Turn it off. Turn it off. Very hot. Very hot indeed. I'll have to change it. I'll have to change the resistors. I can get wire band resistors, the big thick ones, 50 watt ones, which will take it. They're not expensive. I can't afford them like that. This is running at 2.6 amps, and the output voltage is now higher, and the voltage across the primary is obviously higher. Not sure what it is. I can't measure it. I could measure it, but there's a meter here. Could do it. We'll run for a while. I'll run for a short time on this. Not sure I think about it. Put the ice on. It's actually the watch is dropping. It's actually not running very high voltage. It's only one milli. Let's see. Millivolts, 1.1 millivolts. Is it millivolts? 0.1 millivolts, that's 100. This is It's 8 millivolts, 8 millivolts. So it's not large. 8 millivolts. So it's actually not doing very much. I'll put the same thing at some point. It's actually the input voltage is 2.6 volts. 2.6 volts is gone a bit, and the current input current is 3.4 amps. So it's only 6 watts. It's only 6 watts going. That's what it is, and it's actually getting rather hot. So why it should be hot at 6 watts, I don't know, but it is. And the output is what? Let's see the output. Output is so here. Output is 535 volts. So that's reasonable. Reasonable. And there's nothing on the no trace or anything on the utility test. I don't know how I got that result. It must have been 40 about I made a mistake with the connections probably. No, I didn't know what it was. So it's actually 500 watts now. So it's not going up, it's quite stable. And that going up must have been an artifact and not caused by any special happening. That's it. 500. It's going to put it up in a minute. I'll turn it off now, it's getting on. It's the transformer will take it, and the wire will take it. It's actually getting hot this turn. It's actually getting hot. It's smoking. So it's the actual plastic of the mounting board is smoking. It's not the transformer. It's only running at 6 watts. I don't know why it should do that. It's two. It's I squared. Well, it was actually, what did I say? It was 2 amps, wasn't it? So it's 4. It's not huge. I know it's not huge. I don't know what it is, but you see the capacity of the resistor. The resistor just drops the voltage down. So there's that increase in voltage as an artifact, and it only increased to 4 volts. So, but it was probably taking 12 amps, you see. So if I connect it directly, which I can for a short time, it will right down to the transformer. The transformer is actually protected, so it's actually protected, so I won't damage it. So I might connect it directly with but that's quite dangerous. Absolutely. It's obviously not a good idea. That's not difficult. I can use it for a short time to see what the effect is. Let's see. I'll use it for a short time. So I have it set for a short time. Which is the actual currency of the currencies. So the water comes running up for a short time. Actually 7 volts at 11 watts, 11 amps. There's no signal output. And it's actually no increase in signal. So that's how it's probably overloaded the transformer. So bring that way is lower values, which is this one. This is 1 amp at 0.7 volts. It's 0.7 volts. So 1 amp at 0.7 volts. Well, that's less than can't run it high though. This is why I won't take it. I think it's quite fine. I'll measure it. 0.7 amps. So the actual output is there. When I measured it, directly proving it was 12 amps. A short time. It's probably the transformer has a thermal cutout, so it should be restricts it in some way. It's protection. It's over and over voltage. Good. It's now about 50 volts. It's actually 45 volts now. The current has gone down. The voltage has gone down. So it's gone wrong. We don't think these things go wrong. That's with the different reason. I think that's not right resistance. It's not right resistance. I've got my word now. That's actually 10 amps. 10 amps. It's gone down. The actual voltage has gone down. I think there's add this on different settings in that. So you take the voltage when you have the thing directly connected, the voltage drops to about 7 volts, and the actual output is 12 volts. So the voltage drops. That means the thing is staying quite low. But if we connect it to a 1 amp resistor, it would be better, because that's 1 ohm. But for a short time, it did take 12 amps, 12 volts. But it only does that. As I say, I don't want to run it any higher. So the wire on the coil is quite fine, and it will fuse if you have too much current. But I might give the bigger transformer and maybe get that on Monday, because that's a better one. And the other one has a 300 watt transformer, so that's quite high. 300 watt transformer, that would take a current of more, about 10 amps. 10 amp transformer. 10 amp transformer. This one is so the actual idea of the transformer is an ignition oscillator. That's the idea. And it's not driving it. It's not running the thing. That's not the idea. And as I say, it ran quite well before, but I don't know what's wrong with that transformer. I don't know quite what's happening because transformer broke. I can't think. I don't know anything about transformers. So this other transformer, it's a 12,000 watt, not the idea. Running at 1244 watts. That's a lot more. I think I'll measure the size of the wire. I'm going to wire so we'll see what current it will take. It's a ratio of some current, but it will run higher than that. So if I fuse it, I have to replace the wire. But it's only giving an output of 100 volts now. It was 200 before. So obviously something's changed. because I'm using, I did three different values, it's really confusing me. That's like that. Of course, the radiation meter is not measuring anything at all. With the I measured the current in the resonance coil, and and it was the output voltage was 50 it was 100 volts, and the current in the resonance coil was 120 milliamps. So 50,000 times, if it is 50,000 times, let's see, 50,000 times. That's 120 minus 3. The current sheet is 6,000 amps. So if I can induce a current in the plasma, it breaks down, the current is 6,000 amps. And it would be quite a fun. If I look at the calculation, I've got here, where's it here? I've got the calculation here for it. Here. So if we see this will start up probably. If I bring up the resonance, I should put this here. This is a bar, so it should be. Okay. That's all. That's all. That's all. That's all. Let's see how long if we use this one here, it's actually quite straightforward to run this program. Actually, what's it done? It's actually the wrong one. So screw it save. It runs in different directions away. We're going to documents, basic. Read that from there. That should run now. Now just set up. That should work. And this thing's wrong. Not quite wrong. That's wrong. Should let off one drive off. That should be. I don't understand what's wrong with that. It doesn't like it at all. I don't know that. It will run. It will run at all. It doesn't run. It's still in the wrong place. Still in the wrong place. Let's just get back to still in the wrong place. Okay. So yeah. So it doesn't run at all. I don't understand why it isn't running. So the actual diameter of the inner wire is short, 1. So let's see, that's the reference card. Diameter of the former is 28 millimeters, and the length of the former is 40 millimeters, like that bolt. Outside diameter of the reaction tube, well, that's not important, but it's 13 millimeters, and the inside diameter is 10 millimeters. Number of turns is 50,000. Okay, and it gives the inductance 40 ohms, about right, 48 ohms. This is approximate, yes, which is now 22 turns. And inductance run measurement is a foot 48, because I can't measure it, I don't know what it is. And resonant hertz is 50, this is my measurement. I did do a calculation, it comes the right answer. That's 0.2, it's about right, which is what I have. 0.2 is 0.2. The actual crust is 0.2. That's why I know that the gas improvement works. It works quite well. It's the best one. That's right in there. Diode impedance is 30,000, which is when it's a narrow bandwidth. And why do you mass 2 kilograms? Sorry, 2 kilograms. When I put it on, I said it's 4 kilograms. So it's possible somewhere to short it out. It's not using the whole coil. That's possible. Because I had 4 kilograms on there. And it should have been more turns. So I don't know what's happening. I think I wanted kilograms of times. And I had 4. So why it should be only 2. That calculation could be wrong. Q is 2. I was pretty well, but it was 100, wasn't it? 100 watts. And it says the current in here is peak current is 0.8, and the other is 0.5. So it's actually not giving the right answer, so it's not giving what it gives them there. Why it gives 2 kilograms is probably wrong. And the classical current is it's actually giving the wrong answer. So that's right. It's actually a smaller current, that one. So you may have more turns. Maybe the calculation is wrong, you see. Quite right. So the actual calculation was based on the fact that the current was it was 50,000 turns. But when I did the measurement, it should have been 100,000 turns. In which case, it started responding as it should do. And I just wanted it's 4 kilograms, so it should be 100,000 turns, which it could be. And so it gives a different value, and the whole thing flowed because the inductance could be much less than the calculation indicates. I don't know. Usually it's not wrong. I don't know. It's strange. So it could be shorter. Something shorter than the block. But so it's actually quite small. It's actually quite small current. So the whole thing is wrong. This calculation is wrong. It's actually wrong. So I don't know what's wrong with it. Maybe I'll rewrite it, but I need to rewrite it. So I do the calculation again with different number of turns. It's 28 millimeters. This calculation could be wrong anyway. Length of them is 40 millimeters. I don't know what's happening. Let me say that it's actually if I make that 100,000, then it's actually 23k. And when I measured the resistance, it's much less than that. So it's some of the coil is failed. It's shorted, some of the coil is shorted out. So it's reoverheated. It's 193 by simple formula. So there's obviously something wrong. The inductance has failed. The inductance has failed. So inductance I thought is about 48. So it's a sunlight. Arguing about 6 kilograms. That's wrong. I 4 kilograms. So you can work out the number of turns that's starting up. So I know what the number of turns is. It's all going right. It's how nothing works. It's not. So I thought it was. So I thought it was going on. Answering, but this is because it has self-capacitance, so the capacitance is probably more than 2.2 not average. Self-reformer is what's that? And the data formula is 40. It's going to try to outer diameter of the reaction tube is 13. And the inside diameter, because inside diameter reaction tube is number of turns is say 70,000. So I don't know what I could do it by that method. So the gas is now 94. Okay. And so that's what I want to do. And that's what I measured. Rather than put 48, because that's what I measured it. Because it's first of all the capacitance is bigger, that's right. The capacitance is bigger. So the inductance is 94 henries, and it's by measurement it's 48 henries. So something's wrong. Just put that in. Measure frequency 50 hertz. And that's 6.2 again. That's 2. Damn it. Why do you ask? I think some of the coils shorted out. That's what's happened. Half the coil is missing. That means I have to watch the other one. So it's not worked. It's failed. Coil is failed. That's very disappointing. It's what happens with the coil flash that the high voltage short through and it's 100 volts. It's only 45 watts, you see, that's out. Oh, this is wrong. This is wrong. Oh, this is wrong. Oh, this is wrong. Sorry, forget about that. You must have brought it up. That's what I tried. So that's failed. That circuit is failed. So that has to be rebound or thrown away. And it's true till it returns anyway. So let's see if this is turned on. Also, actually realised is making fun. And part of the coin is sorted out, and it's buried inside the coin. You can't get at it. So you've got to unwind it, find where it's broken, where it's not broken or break. It's shorted out. Sort of high voltage has gone through it and sorted out, and all the elements come off. So it was working, but it's not now. And that occurred before I put the capacitors on, I think, because it was. If you work out the inductance from the capacitors, it's 48 henries. It's reasonable, but don't understand it. That's what, if I do the diameter of the card, it's diameter, that's right. But this thing gives a diameter card, I haven't estimated whether that's right or not. So I can't remember how many. But, it's according to the calculation. Well, I had to work out the mass of it. It was 6 from 100 with 100,000. So it's about that was 3, making 90,000. It's just, the resistance writing is 15k, and when I measured it was as far as that. The diameter was 143 millimeters. The fundamental thing is resistance. There's a resistance. That's the absolute resistance of the outer coil. Now it's stripped everything off, and there's a resistance there. This, I did do this at one time. It's actually quite difficult to measure resistance. It's only 4 kilograms. It's only 4 kilograms, and 4 kilograms. So it's nothing like and that is 15 kilograms. So it's actually completely different from what it should be. So some of the guys are so out of strapped. There's too many turns anyway. I have to work backwards for a number of turns and get the right number of right length of wire. And probably, well, I can dismantle it, I suppose. That's possible. If take all the whole thing apart, rewind it. That might be a cheaper option. So it's found. It's found. I don't know what point it's found, but it's found. Circuits found and circuits found have to be rebuilt. This is found too. So this is work that is found. There's no way to figure it out. So there's no way to there's no way so the code is found, and you know, it's true it's a surgical cut. When I measured the calculated cut, it was quite high. The measurement it was high, and I think when I did it again, it's 400 minutes. Any test will be 100 minutes. That's too much. So I had that calculation again. And of course, experimenting, you don't know what the risk. You know, when I did the calculation, I had a different value of inductance and a different value of capacitance. So let's do that again. I'll show you how to do the calculation, which is probably because I did the calculation, it's actually got a different setup. I did experiments to do with my calculation. This calculator may not give the right power anyway. It's getting that. Go to the formula. It was giving very high powers, thousands, millions of watts, but now it's only giving very short powers. So I said, well, it's probably, I may have got the wrong formula. Diameter formula, that's tricky. It over the edge to, that's a 40, so that's, yeah, so the diameter reaction to this. I had to start over again with this. So, I will change. But if it's, I said 50,000, so that gave a, let's see, I want about 50,000. That gives the inductance. So that gives the right value of the resistance. Down is 100 millimeters, so maybe it's only 50,000 tons, and the mass is wrong. But the resistance is 7 over 7 K. So this is right. This is what it gives. So it is right. So it's not this. It's not that. There's several of the calculation. And so I don't need that. So that's right. And the measurement is industrial sort of measurement. But it's not quite 48. But if I measure do the calculation reverse, work out the inductance. I don't know what it is, but it's probably first the inductance comes to 2.22, so the inductance will be slightly higher than 48. I'm going to put 49 down. So and the resistance, and see what it is. And that gives the right answer. It's 49 Andrews, and that's right. So that's right. So it's winding is 2 kilograms. So he may have shorted it out, but it's giving the right values of the so the only 50,000 tons with 2 kilograms. So I don't need such a huge spot, and that would help things. So I'm making another one with 2 kilograms. And that's cheaper, of course, because 2 kilograms of wires is a lot cheaper. It's only about 20 pounds. Now for the IRS potential, when I did the calculation, it was 7 kilowatts. So I put, so that's the calculation for 7 kilowatts. And it does actually make a difference. And the peak current is 0.5, but the IMS is 400 milliamps. So that's how it is. Visual calculation. That's written. But obviously with 100 amps, so you've got a very high current. So I still think the winding shorted out. I still think the winding shorted out. So well, a part of the winding that works is working, and that I don't know where it is. I mean, I could fault find on it, but that's actually quite complicated because I have to wind the wire off. And that's a couple of receptacle for the wire. That's quite difficult. I have to strap the wire otherwise, and I need to have to wire bobbins as well. You notice the difference. The power generated by deuterium is huge. It's 5 megawatts. Power generated by natural gas is 0.1. That's actually some deuterium in it, but it would rise as the deuterium that was generated. But with there, I don't know what the value is, and yeah. That's 400 milliamps. It's high. And I notice that the ampere turns is 28,000. And 28,000. Is that right? As I said, there were 50,000 turns. I don't know all to calculate. When you check a program, you have to do it exactly by hand. It's 50,000 turns times, I've not done this, times the current, which I measured, which I didn't measure, which is there, according to that measure, is 400, that gives 2,000 ampere turns. But it's just about that, so it is correct. And the plasma current is quite high. And the pressure is just the 12 pascals. And it's got reasonable. It's 5 megawatts with deuterium, and I felt I can measure it down to around the point. I may not have as much wire as I thought I did. And that goes up. That's the answer. So it's minute power by natural hydrogen. And I redid that calculation, so it may be giving the wrong answer. And I'm not sure about the power because it's the formula I know, I've got that right, but putting it into reality and set it in the equation, I find quite difficult. You know, it's very difficult things right now. I should really, I don't write them properly. Try to guess, which is not good. So if I go on to the calculation for that, so I can change it. Classic is very good because you can just change it without recompiling it. Yeah, it's the calculation for the inductances, the clouds at the end. So, the power versus power generated. It's up here. It's actually 0.5 watts per cc per kilopascal per kilometre squared, and that's what it is, and that's for cc. So you've got to work out the cc's first. So the inside diameter of the car action tube is in millimeters. I'll get it the right way. It's actually meters because I did the conversion. So we divide by 1,000, get millimeters. No, is that right? Is that right? Wait a minute. Am I doing it right? I've got inside diameter of car. So we begin. Where did I put the inside diameter? So that's interesting. This is where the problem is. Units are usually my weak point, you know. Inside diameter has to be in centimeters, and that means 1,000 times as many as in meters. So if I look up, find out where I put the, it's up at the beginning, isn't it? Where I put the, so it's the delta y, it's delta formula. Outside direction 2, inside direction 2 is actually already calculated in meters. It's calculated in meters. So I want that in centimeters. That's interesting. That's actually much more than that. So it's going to be that's in that the output of that is in meters. So I want to go back to the center. You've got to multiply by 1,000, not divide. Interesting. So that's that actually makes a huge difference. Now I've used a third of the length of the formula because I estimate only a third of it is used. So that should be times 1,000. Interesting. Times 1,000. So if I put that in, so that's wrong. 1,000 times. And the pressure is correct. It's the pressure in pascals divided by 1,000 kilopascals times squared. Is that right? It's per kilopascal. It's the pressure, that's right. And it's the, what's 100 for? If I calculate it, let's get fraction twice. It's so down. 100 times is divided. 100. What's 100 for? What's 100 come from? This is wrong. What was it that from? I'll put 100 the raised to the power inside diameter of fraction 2. Inside diameter of fraction 2. That doesn't make sense. It's formula wrong. It's actually wrong. That's wrong. It's the length of reaction 2. Length of formula, isn't it? That's wrong. It's actually, I need to know the volume. So that's the volume of success. That's wrong. Where did I get that from? That's wrong. Completely wrong. I've got 100 raised to the power inside diameter of fraction 2. That's rubbish. When I get a silly answer. So that comes wrong. And it's got to be multiplied. I've got to find the volume. Let's do the volume first. At the other end, so let's take that out. I'll put it here. Put the volume here, so put the volume calculation in here. So make it in there. Times this and it's times length of formula. If we do it wrong, then we take some length of formula, length of formula, and it's times 1,000 because that's the millimeters. It's times 1,000. That's the length of formula. Right. I don't know what to do there. Length of formula, and it's times 1,000. There's two mistakes. Usually these things are these are mistakes. Although all sorts of mistakes. And divided by 2 to give the effective rate. That's all. So what this conversion, and what that conversion was, I don't know. So there's a conversion there which was nonsense, so like that end of the end was nonsense. So and that was completely wrong, so I don't know how I managed to do that. I'll save it. So run again. So this should give a tiny different result, and the distributed is actually something. So I did. It's confused. See, when they drug you, you get confused. Delta formula is actually what is delta? It's 28 millimeters. Length of formula is length of formula. Length of formula is 40. So inside outside delta. These other things are the same. Outside delta reaction tube is inside number of turns 50,000. Inductance for measurement. I said something. It's still 400 milliamps. It's actually 5.6 to the power 21 watts for the with natural hydrogen. It's 1 times 10 to the 14th, the power 10 to the 14th watts. So it's actually a lot better. But that's a more accurate calculation. So I made some mistakes. This will get right now. So hydrogen is right. And air, of course, has deuterium, which is where the power is coming from. But, and that's where the coil is it is, and the resistance as it is. But I'm no way, it doesn't look as if I haven't got so many turns as I thought. I need to measure the diameter of the coil. Something's wrong. I thought I'd put 4 kilograms on, but since I only put 2 kilograms on, which is a lot less. So the half the cost is great. I don't have that. I don't have that. So that's interesting experience. I now measure the diameter of the coil to see whether in fact it's got 50,000 turns or 100,000 turns. Because it's obviously, I know what it is. I'm going to measure this what it is. I know where the coil comes to. I'm going to get some estimate of the diameter of the coil. It comes to there. So get some idea how big the coil is. don't know what it is. It's probably short enough. So it's from about there, and that comes out there. It's actually that's like that. It all comes out. There's a carbon. That is the carbon. So it's 36. It's actually, is it about 100? It is 50,000 tons. But why do you swap it? It must have been used 2 kilograms. Weird. So I've done, somewhere along the line, I've done the calculation wrong. So it is not, it's alright. That doesn't look alright. It's 50,000 tons. As I say, it's 50,000 tons. And it fits on there nicely. And it's 2 kilograms. I'll remind you the weight of the coil is not being weighed, it's just down the calculation. And that's from the volume of copper and the mass of copper. And that, all that could be wrong. So, sorry, errors could be made. But it looks like the power's a lot better. That will account why I'm working with this explosion. But it has to start up. Now, if you can start it with 12 volts, that's fine. But it's it's obviously different, and then the result is different this time. But although I had a higher voltage last time, it could have been anything, couldn't it? So I still might need the 400 amp oscillators. It might still need it. I'd like to use a smaller, because I'm using that's 12 volts, but that's a 12 volt 400 amp amplifier. That's estimated, but maybe it needs as much as that. So if I can get it, so the moment I've got 400 volts I got from that, didn't I? So if I can get that's with 3 amps, so just a calculation. So it's 400 amps, and times 5 divided by 3, literally 600 watts. So if I can increase the current to 5 amps, it'll be 600 watts. And twice that, it'll be 1,000 watts, which is more likely to strike. So I need about 10 amps. Now, the next thing to do is to measure the size of the wire. I've got a fairly inaccurate, because I need to know what this is. I can't just fairly heavy wire, it's not too bad. But I selected it as a 3 amp wire, because I thought I would use it as output. So if I could put in a winding on it, and just take this heavy coil. Essentially, it's 1 millimetre thick. 1 millimetre thick. So what does 1 millimetre thick wire take? 1 millimetre diameter coil will actually take quite a lot, won't it? Let's look it up. I've got wire tables here. Wire tables look up the thickness of the power of 1 millimetre. I remember I didn't sure I measured it. Sure. It might take, what does it take, Charlie? I do like this a short time. For our beads. There's a wire, this is log tables. Or fuse wire. Fuse wire rating. That's interesting. But that's very fine. This is obviously different. So let's look my side this way. So 1 millimetre wire. It's actually got it in SWG. And the current rating is all in SWG. And the diameter is in in inches, so we have to look it up somewhere else and get the millimetres, which is what 1 millimetre is. 1 millimetre, and that's 19 gauge. So look at them here, 19 gauge, 19 gauge. It's like they've got 18 gauge, and that's and the current rating is 2 amps. 2 amps. So we take 3. For a 10 amp wire, it's 12 gauge wire. Put that up here. 12 gauge wire. It's 2 millimetre wire. And yes, it needs 2 millimetre wire. So I'll have to wire some 2 millimetre wire on to get the current. But I don't know whether in fact it would start at 12 volts. But that's right. So if I do the calculation, that's 1,000 volts, 1,000 volts, and that may start it. So it'll take it for a short time. It will move wire take a short time, so I could test it on that. So what I need to do is to take off this very heavy coil and so this is I need to know how many turns to put on. That's the other thing. I don't know. But to get a 30, see if I've got 50,000 turns on there. 50 there, so 1,000, I probably have 50 turns, so 1,000 turns so much. So if I put 10, 12 volts on it, I should get 1,200 volts out there, and that does seem to work. So I need 10 turns of 2 millimetre wire. Well, that's not many turns. And it will probably be put on by hand without putting on the coil winder. So if I take off that very heavy wire, but I won't put it over the top actually, because that would put something around it, tape around it, and then put the wire over the top to prevent that from happening. So I can leave the winder winding on there. Exactly that's thing to do. So that's how I work. There's a series of steps, guesses, calculations, and trial and error, basically all the time. And you don't know until you've done it what's right. And you've got the basic calculations, you've got the formulas for ratios and things, which because you're dealing with unknown, you don't know what when I did the calculation, when I've done that before, it was a much bigger machine and it needed 4 kilowatts. But if it were doing 144 watts, that's a lot better. And so I think I'll buy the other transformer. And that's sort of got the top one. The only one that's another £10, I think. The total is it. It's time I cook it, otherwise it's really heavy there. And I should really know. Well, I can't change it today because I haven't got £10. So I'll let it go on. And he won't be there tomorrow. I'll leave up, see if he's there. So that's what's wrong. So that's how I do the calculations, and that's how I do the calculations, and how the formulas are adjusted on the fly according to the results of what's reasonable. And also I made a mistake with the power level because I have a funny formula for the answer, and that was right. I know where I got that from. Well, I'd like to bring somebody else to post it, but I don't remember because it's a silly formula, so it's possible somebody else put it in. But it's obviously wrong. I where I got that from. And so it's the area of wind by the volume. So I think they've got that right. So it's pi r squared and then times rate.